Solving first-order linear differential equations by the method of integrating factors. First-order linear differential equations are just a type of differential equation. It differs in that you can't solve it by separating x and y into different sides of the equation and integrating to find the solution equation. You have to go about using different methods. One method is the method of integrating factors, and this method uses an integrating factor called mu to find the solution equation. For this method to work, the differential equation must be in the form y prime plus p of x times y equals q of x. Now, a lot of times it may not be explicitly expressed in this exact form, but as long as you can rearrange a differential equation into this form, then you can use the method of integrating factors on it. Mu is the integrating factor, and it is defined as e to the integral of p of x dx. Right now, we're going to find the derivative of this mu early on, because it'll be a lot helpful later if we do the derivative right now. So mu is expressed as an exponential, and we know how to deal with exponentials and taking the derivative just by using the chain rule. And so we can see that the derivative of mu is just p of x times e to the integral of p of x, because the derivative of an integral is just the original function. And so mu prime equals p of x times e to the integral of p of x. And we can also notice conveniently that e to the integral of p of x is what mu is defined as, so we can say that mu prime equals p of x times mu. Now that we've done that early on, we can find the derivative of mu times y. This might seem random at first. Why would you just pick a derivative of mu times y? But if you just take a close look at it, you can tell that if we actually find what that equals, then you can just take the integral of both sides, divide by mu, and you have your solution equation. So we're going to take the derivative, and we have to use the product rule. So that would be mu prime times y plus y prime times mu. And we know mu prime is p of x mu, so we can use substitution, so that the derivative of mu times y is y prime mu plus mu times p of x times y. Now we want to factor out mu, so the derivative of mu times y can be rearranged so that it equals mu times y prime plus p of x y. And we've already defined that when you're working with this integrating factor, that it needs to be of the form y prime plus p of x times y equals q of x, and we see right here that that's already come up in our differential equation. So we can just substitute q of x for the inside of the parentheses, so that the derivative of mu times y is mu times q of x. Now we integrate both sides so that we get mu times y equals the integral of mu times q of x dx, and we will divide both sides by mu, and we get y equals the integral of mu q of x dx, all divided by mu, and we can take that mu out, so it's 1 over mu, just to make the equation look better and make it easier to deal with, and we arrive at our final solution, y equals 1 over mu, the integral of mu q of x dx. Now let's do an example and find the solution equation of a first-order linear differential equation using the method of integrating factors. We'll use the example y prime plus 3y equals e to the negative 2x. You can see that this equation is already in the form that we need, so we can just start off by identifying the variables. The first variable, mu, we can save that for a couple seconds because we need to know p of x and the integral of it. And we know p of x is 3, and q of x is e to the negative 2x. So mu must be e to the integral of 3 dx. The integral of 3 is 3x plus c, so mu is e to the 3x plus c. However, the c would normally be brought down to the front, but in this case, we know that mu later on will be used in an integral anyway, and we can save that c and combine it into the big C at the end. So for the purpose of mu right now, we can say mu is e to the 3x. So now that we've defined p of x as 3, q of x as e to the negative 2x, and mu as e to the 3x, we can just start filling in the variables and soon arrive at the solution equation. So if we plug in the variables, you get y equals 1 over e to the 3x times the integral of e to the negative 2x times e to the 3x. And we know by the rules of exponents, we can combine the two e to the x's just to be e to the x, because negative 2 plus 3 is 1. So, and we also know e to the x is its own integral, so we can easily simplify this integral to be e to x plus c. So our solution equation should read y equals 1 over e to the 3x times e to the x plus c. We can do a quick distribution, and we get y equals 1 over e to the 2x plus c over e to the 3x. This method is really fast, and the really well-chosen integrating factor is what developed this whole method.